It's time for another chemistry video. So I've been following Chemistry, the Central Science, a textbook. We're in chapter 14, which is on chemical kinetics, the rates of reaction change and so forth. And so this is the second video on the change of concentration with time. The previous video was on first order reactions. This one's on second order reactions. Let's dive right in. Okay, so for first order reactions, let's do a quick review. So the rate of change, the rate of a reaction is equal to the negative of the change in concentration per time. Change of concentration, if something's decomposing, then this is negative. It's getting smaller. The concentration's getting smaller. The reaction's moving on. So this is negative, but by convention we want rates to be positive, so we have to take the negative of a negative and get a positive. All right? And it's also equal to a constant times the concentration of A. This is called a first order reaction because the power of the concentration of A here is 1. When you don't write anything up here as a superscript, it's 1. That's assumed. If nothing's written there, the power is 1. And so that's a first order reaction. And what we found in the previous video is, the thing about this is, it doesn't involve time. So if you know the concentration, then you can say what the rate is at that particular time. Or if you know what the rate is at a particular time, then you can find the concentration and so forth, if you know K at that temperature. So, but this is a fairly static thing. It doesn't say in 3 or 4 seconds, this is where the concentration is going to be, or in 3 or 4 seconds, this is what the rate is going to be. It's a fairly snapshotty, static thing. So what we did in the previous video is we found out that if we can bring the beginning concentration, beginning concentration, concentration of A sabot, or the concentration at time t, which is concentration of A sub t. T is the amount of time that's elapsed. K is that constant at that temperature. Ln means natural log. And I said in the previous video that if you don't remember what natural log is, it doesn't matter, your calculator knows. Plug it in. So there are 4 variables here. The concentration at time t, the initial concentration, the amount of time elapsed, and the constant. So you have 4 variables here. If you know any 3 of them, you can solve for the other one. That's the previous video, so that's all review. So now let's talk about second order reactions. Let's consider a very simple second order reaction. So nitrogen dioxide decomposes into, I think that's nitrous oxide or nitrogen oxide, and then plus oxygen. So this is why is this simple? Because it only involves one substance. How do I know it's a second order reaction? Well, it has to be determined experimentally. There's no way to look at this formula and say, oh, that's a second order reaction. You just have to experiment and find these things out. But this is a second order reaction, which means that the rate is proportional to the square of the concentration. This is the rate proportional to just the concentration. This is linear, but the rate is proportional to the square of the concentration. So the rate is equal to the negative of the change in the square of the concentration per time. Or you can put it this way: it is a constant times the square of the concentration. And so you can see the 2 there. This is a second order reaction because it's raised to the second power. But it's simple because we don't have a substance A and a substance B. So we're going to start with something that's simple. All right, so what is the integrated rate law for this? The integrated rate law, again, like this top one, this doesn't involve T, and this doesn't involve T. And so how can we figure out what the concentration is at a particular time t for a second order reaction? There's the answer. This actually is easier than the previous one, which involved the natural logarithm. So the first order formula is actually more complicated than the second order. And this is in the form of y equals mx plus b, by the way. So this is linear. If you plot your experimental results and the natural logs end up as a line, that tells you it's a first order reaction with the natural logarithm of the initial concentration as the y-intercept. You know, y equals mx plus b, negative k is the slope, and then the natural logarithm of the initial concentration is the y-intercept, as it were, the b. So if you plot experimental results and it ends up that this is a line, you have a first order reaction. Well, for a second order reaction, this is also a linear equation. And so if you do some experimental experiments and you plot the graph of this equation and it comes out as a line, then you know it's a second order reaction. 1 over the concentration at time t equals the constant times t plus 1 over the initial concentration. And like I said, this is also linear. Now, so what do you need to take from this video? This is what you need to take from this video. You should know this particular equation for a second order reaction. Like I said, there are 4 variables here. If you know 3 of them, you can solve for the other one. So if you know all 3 except the concentration at time t, you can solve for the concentration at time t. If you know all 3 of them, but you don't know the constant, you can solve for the constant. If you don't know how long the reaction has been going, if you have all the other variables, you can solve for the time. Or if you know this other stuff, but you don't know what the initial concentration was, you can solve for that. So that is the integrated rate law for a second order equation. And you can turn off the video now if you want. But for those of you who like calculus, I want to show you how this was derived because I'm a nerd and I like that stuff. So to get this equation, we start back here. We've got this thing here. And what we want to do is we want to integrate with regard to time. We're integrating both sides of the equation. We're integrating one side in relation to concentration, and we're integrating the other side in relation to time. So if I'm going to integrate, first of all, let's get rid of the deltas and make them instantaneous, because the deltas involve averages. So that ends up with, in calculus, a d concentration squared dt, all right, equals k concentration squared, and so forth. So then what I do is I'm going to take the integral of both sides, but I'm going to shuffle some things around. So I had k concentration squared on this side, right? So I divide both sides, and I get the concentration squared down here. I had a negative up here, bring it to the other side, and then I had a dt in the bottom, bring it up here. And so this is simply a rearranged version of this down here. Okay, but once I get it into this form, and I'm going to integrate from the initial concentration to the concentration at times t. So once I integrate both sides, I get the formula. Because if you know basic integral calculus, the integral of a to the minus 2 power, and an a squared in the denominator is a to the minus 2 in the numerator, right? So to integrate from minus 2, I'm going to go to minus 1. I'm going to have to put a minus out front so that it cancels out if I go the other way. Anyway, the integral of x to the minus 2 is negative x to the minus 1. I'm not going to go through it. That's calculus. But so this is x to the minus 1. And there's the negative out front. And then I'm going to do it from, again, the initial concentration to the concentration at time t. I'm going to plug these in to this. And so equals negative k, and then the integral of dt with regard to t is just t, right? So I've got this side here, and what this is going to be, I don't think I wrote it out, so I'm just going to tell it to you verbally. It's when I plug the at in, it's going to be 1 over a at time t minus 1 over a at time 0 equals kt. And then I'm going to add 1 over the concentration at time 0. It's going to cancel out on this side, and it's going to end up on this side. So I'm going to basically end up, so the negatives cancel out. Kt, there's the kt. When I plug that in, it's going to be 1 over a to t, and then I'm going to add this to both sides, cancel on this side, and it'll be a plus on this side. So that's how you use calculus to get this equation right there. But you don't need to know that. Just know that this is the integrated rate law for a second order equation.